2:30. I think we can get started. Yeah. Yes. Again, thanks for coming. This is the January Research and Technology Forum for the Syracuse Center of Excellence in Environmental and Energy Systems. And we're so happy that today we have Professor Wei Zheng that giving us a talk on nanotechnologies for renewable energies. Professor Zheng is a faculty in the Department of Chemistry, and he has done a lot of fundamental research in materials, sorption materials, metal organic frameworks, including for both energy and environmental applications. And he has received many research grants, including the National Science Foundation Career Award. So I will leave that rest to Professor Zheng. Yeah. Welcome, Professor Zheng, for the questions.
All right. Thank you very much, Jason, for the introduction. And I'm very delighted to be here to share something I'm really passionate about, which is the field of semiconductor and for energy application. Okay, so we're trying to ask a broader question: how can technology address many global issues like environmental pollution, air pollution caused by use of fossil fuels? One promising solution might be how about the use of greener energy resources like solar energy, right, to replace the fossil fuels. In fact, material chemistry already, chemists already, use nanoparticles, nanotechnology to make some of the, such as solar panels, sensors, LEDs. Right now LEDs everywhere. You can buy from Walmart, Lowe's, Home Depot. We have many sensors to detect the pollutant in the environment. But how about the solar panels? We already proved the concept. It's beautiful, right? But today is a beautiful day. I think mostly, sunny day today, right? Why we don't see solar panels everywhere? So can you see the problem here is we have a limited efficiency for these new devices for green energy harvesting, and so another issue is the cost, right? It might cost too much. No one want to pay like tens of thousands of dollars buy a solar panel on the roof. They still need to pay $200 utility bill every month, right? So okay, to use this new technology in our everyday life, we need to improve the material design properties and make better devices. But I'm in chemistry department and many focus on fundamental research. Okay, so the nanomaterials I'm interested in, they are semiconductor nanocrystals. Basically, semiconductors on nanoscale. Can be spherical particles or quantum dots, can be one-dimensional rods, two-dimensional films. Okay, so those nanomaterials, they are unique size-dependent optical properties. Okay, for example, for many 2,6 group compounds like cadmium selenide, cadmium sulfide, zinc selenide, etc. So you can see smaller particle they have a larger band gap. Okay, so they can emit light with a higher energy, which is blue light. Okay, and if you increase the size, you have a weak quantum confinement effect. If a smaller band gap, they can absorb and emit light with a lower energy, can emit the red light. So you can see simply by changing the size, you can tune the color emitted in a full visible spectrum. So this is because of quantum confinement effect. That's why initially we called them quantum dots. Okay, so that's pretty unique, right? It's usually not being observed in both materials. For example, in our table here, if I use the chainsaw, cut in half, I get two small tables. But you're not going to change many physical and chemical properties. The color, mechanical properties, hardness remain identical. You just get two small tables. But when you go to the nanometer regime, you reduce the size, you change the energy, you change everything. Okay, that's the unique property about nanomaterials. And there were another feature of material properties, for example, broad absorption, can absorb more light from the solar spectrum, high fluorescence, quantum yield, and much better photo stability compared to traditional organic dyes. Okay, because of this, excellent property, there are wide applications. It can be made, soft screen. Can be used to fabricate palm dot-based TV. I think already commercialized by Samsung. It can also be used for solar panels and photocatalysis. Okay. Our group does a variety of things. I thought I can use one slide to show you what can we do and what can we learn, in the past few years. Okay, thank you. Yeah, summary 4 research directions. We always start with sample fabrication or synthesis. So for example, recently we developed a self-assembly method to make a 2-dimensional peroxide platelets by assembly for 1-dimensional nanorods. So after synthesis, we go to materials characterization. So in addition to size and shape, we want to understand microenvironments. For example, surface states, interface, right? This is a very interesting area. We developed a very sensitive optical probe to allow us to tell the difference between the surface, atoms, and the atom in the interior, in the core of nanocrystals. Okay, and even the interface for some coherent structured nanoparticle. After that, we move to the properties. How can we engineer the nanoparticles have a better performance? Right? So we have 2 strategies. One is engineer the inside, interior particles by introduce dopants, by changing the chemical composition. Okay, we can by introduce dopant, we can tune the optical properties and the magnetic properties. Okay, so another strategy is opposite. We can do surface modification. We can engineer the material from outside. We do surface encapsulation, can make a hybrid nanocomposite. For example, peroxide materials, they have a very limited stability. Even those, green material, many excellent properties I'm going to show you in my today's talk. So, but they have a limited stability. So what we did is we developed an oxide shear coating method. We shear with titanium dioxide. We enhance the stability, and also we include the charge transport properties for photocatalytic reactions. So here you can see the brief picture about our research. In the next 15 minutes, so you try to touch each of them with one example. Okay. So here summarize 3 synthetic methods in my research group. We work on traditional colloidal synthesis. It's a very simple setup. Glassware is heating metal provide heat. Thermal method make it a particle, but we can make beautiful particles. We're also interested in greener synthetic method. For example, photosynthesis. So sun is a greener energy resources, right? We can use the sunlight to drive chemical transformation. And here's a photocatalytic reactor on a hot plate. You can read 4 reactions simultaneously. Here, integrate with the LED chips, you can choose a different wavelengths for photocatalytic chemical reactions. Okay. We're also interested in some reactions under extreme condition, like high temperature, high pressure. If we use water as solvent, this they call hydrothermal reaction. If we reaction in organic solvent, they call solvent thermal reaction. Okay, you can go to pressure up to like 1,000 atmospheric pressure. So because of a high ion diffusion rate under those extreme conditions, we can achieve some unusual phase structures of nanomaterials, which is usually not easily obtained under ambient conditions. Okay, here I show you a couple of examples. We use the colloidal method, make a magneto and the particles. Example here is magneto and sulfide quantum dots. We introduce magnet dopant there. We introduce impurities into nanoparticles. Okay, the first you might ask, why you want to introduce impurities? Are impurities bad for nanomaterials? Well, it depends, right? So if it's bad impurity, we usually call it contaminants. If it's good impurities, we call it dopants, right? Modern semiconductor industry, spend $1 trillion every year trying to make an N-type and a P-type doped semiconductor material, right, for electronic devices. So this is we introduce good impurities called dopants. Okay, the reaction is very simple. You can see, final product of manganese pentasulfide quantum dots, 3 elements in the product. We use the manganese nitrate as a precursor for manganese. Cadmium, we use the cadmium nitrate. It's organic solvent. High temperature, we inject the sulfur solution, which is an organic solvent as well. If you don't let the reaction go too long, too hard, you can make a nano. Actually, it's very simple. My undergrad student can make nanoparticles in my group. So you can see this is a TF image for manganese pentasulfide quantum dots. Okay, spherical particles. Okay, but because shape also very important for properties, and we can also make a one-dimensional nanowire. For example, this is silicon nanowire doped with manganese. Okay, I didn't show the synthetic method, but for the 2 samples, I use almost identical procedure to mix them. Okay, exactly the same thing here. Cadmium sulfide, I use cadmium nitrate. Here, I use zinc nitrate. Here's a sulfur powder. Here, I use a selenium powder. But why in this case we make a spherical quantum dots? In this case, we make a one-dimensional nanowire. It turned out that the host lattice, the structure of the host lattice, is a key parameter to tune the final morphology. Okay, in this case, cadmium sulfide is a cubic phase. ABC equals 90 degrees between 3 axes. Right? You don't have a structural anisotropy. You make a cubic phase spherical quantum dots. And here, this one at the host lattice woolsite phase or hexagonal phase. They have a longer C-axis. You have structural anisotropy at atomic scale. So that's why that dictates the group's behavior of your nanocrystals. So you can make a one-dimensional nanowire and nanorock. We can also make a 2-dimensional nanoplatelets or nanofilms. For example, this one. But in this case, I have a cubic phase. Now, how can we do shape control for cubic phase nanomaterials? Right? Can you imagine it's not easy, right? Don't have a structural anisotropy. But for peroxide materials, most optical active phase or good phase are cubic phase. Right? So this is a challenge. Okay, before I talk about how we did this, briefly talk about the metal halide peroxide and crystals. This is the fascinating materials. And first synthesized in 2015, those metal halide, peroxide on nanoscale, you can see, by changing the halide composition, the chloride, bromide, iodide, you can tune their band gap, you can tune the color emitted in a full visible spectrum. In addition, they have a superior excellent charge transport properties. Okay, you can, you have a very efficient charge transport, you can understand it might be very important for photovoltaic applications, right? So you can manipulate the charge carriers. Yeah, also for high emission quantum yield, etc. Okay, so this is the structure of the metal halide peroxide materials, right? So the left side is the B side sitting in the center of the octaedron formed by 6 halide ions, and the cesium sit in the big hole between 8 octaedron. Okay, you can see it's a cubic structure, right? So excellent properties. You can see many good papers out related to peroxide every day. But there are 2 problems related to peroxides fundamentally. So first one is, as I said, cubic phase, how can we do shape control? Okay. And second question is very limited stability of a peroxide material due to their ionic nature. Most common example for ion compound is sodium chloride, table salt, right? You can put table salt in water, boom, they gone. Right? You can see because of the ionic nature of a peroxide materials, sample degradation can happen, under a couple of conditions like, heat, UV light, air, oxygen. So that makes the sample, fabrication, storage, and device application very challenging. In addition, the lead here is highly toxic. It raises some of the environmental concerns, right? So you can see those are very important questions we need to address. We need to answer one by one. So first one, how to shape control for cubic phase peroxide nanocrystals. Okay. So one thing we based on the crystal groups, we know even so cubic phase, if the surface energy along different facets are different, you can have a different crystal growth rate, right? You can have an anisotropic nanocrystal form if you can tune the surface energy. So what we did is we developed ligand mediated growth and assembly strategy to grow non-spherical cubic phase peroxide nanocrystals. So idea here is if you can selectively, absorb some certain ligand on the surface, you can change the surface energy, right? What we did here is we introduced a mixture of ligands. So basically two types of ligands. So one is the long ligands, or like acid or amine, they have 18 hydrocarbon tail. These are organic molecules. And another set of ligand is a short ligand. All acid only have 8 hydrocarbon tail. So our idea here is the short ligands bind on the side wall with higher packing density. But long ligands, bulky, they bind on the tips with larger free volume between them because of a steric effect, where we need more space. So then you have a different surface energy and side wall being protected, lower energies on tips, more free volume can keep adding reactant on tips, it can boost one-dimensional nanorods. Okay, that's our idea. Okay, later I think when we form one-dimensional nanorods, we can use this to form 2D nanoplates by material sampling. Okay, we think it's a ligand-mediated behavior because high packing density on side walls, you can have non-polar interactions, van der Waals interactions, right? But if we know van der Waals interactions is not primary bonding, is very weak, we want to give them a little bit of help. So what we did is we put in autoclave. We apply pressure. We force them to fuse together to form 2D materials. Okay. Now here, just quickly give you the results. Indeed, when we introduce mixture ligand, we tune the surface energy. We can put one dimension in the words. Then we transfer to autoclave, apply pressure. We can make a sphere like nanoplatelets. So interestingly, as we further increase solvent thermal reaction time, this small nanoplatelet can further assemble together by lateral fusion and Z reaction stacking, can form larger nanoplatelets and even big nanosheets. Okay, so before our work, the people can only directly make silicon lead bromide 2D materials, and we found this is a general method. We can make all halides nanoplatelets. We can make the silicon chloride, bromide, iodide, everything. So this is the first general method to make a 2D peroxide nanomaterials. Okay, so we addressed the first question. How do shape control for cubic phase peroxide? Now let's move to stability. Okay, how can we make more stable ionic structured peroxide? Based on our experience, if something not stable, one straightforward is by subject coating, right? Like this table. You put a pen on it. Right? One thing make it look nicer, but it's much more stable. Okay, much water not going to penetrate in the wood, last longer. Right? So then how about do certain modification? And we know they're not be stable in air, in oxygen. If something done stable, not stable in air, most likely it can be react with oxygen from oxide, right? We thought, how about we brew oxide on the surface? How can it be oxide, right, in air? So that's what we did. We brewed titanium dioxide on the surface of a peroxide nanocrystals. But that's not a challenge here in chemistry synthesis. We want to make a oxide. Usually start with metal precursors, and in water solution under hydrolytic reaction. We know peroxide have a very poor stability in water. How can we do hydrolytic reaction in water, right? So then what we did, we actually did hydrolytic reaction in non-aqueous solutions in poly. Okay, we start with the titanium precursor. We do very slow hydrolytic reaction. In polyene phase, we control the moisture level to 30%. That's very dry, right? In Syracuse in winter, if you have a very dry air, if you itching of the skin, humidifier in my room. Otherwise, I feel very uncomfortable, right? We do hydrogen reaction in very dry condition. Then after that, followed by thermal cancellation, 300 degrees Celsius, we form crystalline phase TiO2 cold materials. And we found whenever we can significantly increase the stability, we can also improve charge separation efficiency. Okay, so here just give you one example. We did, several stability tests: air stability, light stability, chemical stability. Here just show you a water stability, because this is the most big challenge for the field. You can see without shaded coating, if you put in water a few minutes, it's gone, like a sodium chloride, a table salt, right? If you're dry powder, it can last a few days longer. In 3 days, almost gone. If you share with titanium oxide with a amorphous phase, they can stable for about a week. But after thermal calcination, we form crystalline phase TiO2. They can be stable for at least 3 months. You can go further than that 3 months. We saw in the paper at that time, this is the most water stable peroxide-based material report to the community. But right now, probably a new record. So that's what we did. Okay, you can see this is a TEM image. Okay, which is great. We found it can be useful for the texts. Okay, but when we look at TEM image, you might notice, you can see sometimes TiO2 wrap 1 peroxide and particle inside, sometimes wrap 2, sometimes wrap 3. Okay, and you look at here, not symmetric shell or not uniform thickness for TiO2 shell, right? This side, the thicker side is thinner. The reading here is this is not epitaxial groove of shear materials on substrate. This is just like you wrap it. Okay, you like a wrap a plastic bag, you wrap it on the surface. This is a very fast reaction. So you can see the shear thickness is not uniform. They are not monodispersed cultural particles. So that can cause problem for industrial application, right? Monodispersed particles of thickness lead to monodispersed properties. Even wide distribution of how many particles wrapped inside of shear thickness, you can have a wide range of properties. It's hard to apply. So we think, how can we epitaxially groove a shell on peroxide with a uniform shell thickness, right? But that's a very challenging. Really, here is culture increase is not new, but if you want to groove core and shell epitaxially, you need 2 requirements. First, core and shell have the same crystal structure. Secondly, they need to have a very similar lattice parameters or very small lattice mismatch. So you can group atom on top of atom, right? Very similar structure, similar space between atoms. But a peroxide, you have a very large lattice parameters. Okay, it's very challenging to group not a semiconductor on top of a peroxide due to large lattice mismatch. So what we do is, we thought, we can group not a semiconductor on top of peroxide. How about group peroxide on top of a peroxide? Okay. Specifically, we want to group double peroxide on top of a peroxide and the crystals. You can look at the formula, right? This is signal 1 that highlight 3. This is signal 2 highlight 6. It's double, right? Basically double. If you look at this, you might say, no, that's mission impossible. Double peroxide have doubled lattice parameters, a huge lattice mismatch, right? You think, no, we cannot do it. But when we look at the structure carefully, we found, no. If you look at the structure here, right side is a simple peroxide, left side is a double peroxide. Okay, so basically, you replace 2 labs, which is it's octahedral corner shell octahedral, 2 labs with 1 T. Okay, you create additional vacancy here. If you look at the arrangement of lab and T, they are way different. Okay, that parameter 100% different. But if you look at arrangement of the highlights, small highlights, they are identical arrangements between double peroxide and peroxide. If you look at the cesium arrangement, big blue sphere, they are identical. So if you calculate lattice mismatch based on halide and the cesium, very small, less than 10%. So we thought we might be able to do it. Okay, we would definitely, hand in the back. He worked on the project for a year, and just give you final results. Top row here is TM4 whole nanocrystals. This is the sodium, bromide, iodide, and bottom is calcium nanocrystals. Okay, you can see, size usually increase from less than 10 nanometers to about 13 or 20 nanometers, or a few nanometers, and uniform shear thickness. So the higher resolution TM can prove they have a slightly different lattice parameters there, but pretty solid. Okay. And depending on the halide composition, can have different types of calcium nanocrystals with different optical electronic properties. For example, for sodium lead chloride here with sodium chloride calcium nanocrystals, they're type 1 calcium nanocrystals. Here's a band alignment. Basically, the band gap of the shear materials are much wider than the core. Both electron and holes are confined with the core materials. So basically, shear just act as a protection layer. You're not going to change the charge carrier properties. But in this case, because the shear protected, more stable, there are much higher emission efficiency or emission quantum yields. Okay, same situation for sodium bromide and sodium bromide calcium nanocrystals. So you can see in this case, they're very promising for LED application. You want to make a very intense light emitters, light devices, right? But for iodide-based calcium material, you can see you get type 2 calcium. This is the band alignment. So basically, not shear that wider, they are staggered band alignment. So the conduction band edge from the shear is lower than that of the core. So basically, electron are going to go outside. Electron can migrate outside to the shear, and holes can stay here. So you can see I can physically separate electron and holes at different location of the calcium nanocrystals. That can be very interesting or promising for photo attack or photocatalytic reactions, right? Yeah. Okay. So this is a synthesis, stability and shape control. Now let's move to microenvironment nanocrystals. And why do you talk about microenvironment? For example, surface space. Okay, surface or interface is extremely important for many functional materials, right? Surface, basically keep things in and out, right? So we're mass transportation, thermal transportation happens, right? And also can initiate and stop reactions, as the case in photocatalytic reactions and corrosion. Where corrosion happens, surface, right? And we know surface and the atom inside, they have a way different chemical environment. For example, atom inside the particles, they form more bonds, highly saturated. Okay, atom on the surface form less amount of bond. For example, if I'm certain atom looking down, find a neighbor, look up, empty. Right? The atom inside the material, look at around all neighbors. Right? So then certain atom form less amount of chemical bond, more reactive, because bond formation is a exothermic process, release energy, right? Now you form less bond, more bond, more reactive. That's why we can use small particles, certain atom for catalytic reactions. Okay, so this is a theoretical model for 1 nanometer quantum dots. If you count how many atoms on surface, more than 30%. So you can see this is another unique property for nanomaterials, high surface to volume ratio. Okay, that's why nanoparticle can be serve as a very robust photocatalyst, right? Okay, so now we know surface is most reactive, the definite relationship between microenvironment and their final properties. But if experimentally, how can we prove that? How can we study that? It turned out that it's very challenging. To study nanoparticles is not easy because it's so small. Now you talk about a microenvironment, probably only one more layer of the atoms. Or maybe if you atoms, we talk about on edges or corners, right? So before I show our approach, I like to use a double game table tennis as an analogy to show our approach. Okay, two reasons. One, people that ball is very small, sometimes hard to see from audience. Same here, small particles. Two, I think I've seen most of you might know how to play table tennis in a simple way, but double game is more complicated. Most of you might don't know the rule for double games. Okay, but if you don't know the rule for double games in table tennis, you want to learn. How can you learn? Some of you by watching TV, see how professional players can handle balls, right? Yeah, you can, but the ball is very small, probably take a few hours to figure out the rules. But I think more efficient way to learn rules maybe by direct precipitation. Direct precipitation. I'll give you a pattern. You hit the ball on the table. After a few matches, if you violate the rule, you can lose points. Right? You learn from error, you can after that definitely very confident to tell me the rules. So I think, instead of look at those tiny particles on a microscope for like an hour a day to hard to find the rules, why not send players or atom there? Let atom tell me, do you feel any difference? Okay, so that's what we did. So now, for example, if you want to understand the surface and core environment for cadmium selenide quantum dots, this is two-dimensional illustration for nanoparticle. Now, how about introduce a magnetic dopant? The magnets, right? It's magnetic, here's spin here. Some magnets on the surface, some magnets inside the dotted circle here is magnet inside the core. There are different coordination environment. Inside saturated, outside unsaturated bond. Okay. Now we can use EPR, electron permanent spectroscopy, to look at the different microenvironment for those magnetic dopants. Okay. EPR, I'm not sure, probably most of you don't do EPR. The concept is same as MR. MR is more popular. The MR, you're detecting nuclear spin. In EPR, you're detecting electron spin. Similar concept. Okay. If you don't work with magnetic EPR, it's okay based on the spin quantum number, nuclear spin quantum number, simple rules. You're supposed to have 6 peaks. Okay, from EPR. If you know 6 peaks, you can understand this slide. Okay. And we did the EPR measurement fund, we have more than 6 peaks. But we can simply fit data to 2 sets of 6 peaks. Okay. So this data is same as magnet-doped bulk materials. Okay, largely inside the core. And this side higher energy shift to high field, that's magnets on the surface. So we can use the magnets at optical order to detect the microenvironment, surface states, interface state of a nanoparticle. Okay. All right. So let's move to the properties. Okay. How can we engineer the nanoparticle for grand energy application? Okay. Solar energy is so great. We want to use this, right? The broad solar spectrum. Can we use quantum dot nanoparticles? For solar energy conversion, can we, the idea sunlight absorber. They can absorb sunlight for sure, but they are not ideal. Okay, I'll show you a problem. This slide. So, for example, this is the absorption spectrum, dot line, and emission spectrum, which is a solid peak here for zinc selenide quantum dots. Okay, I highlight the spectrum. Some spectral overlap here. Okay. So you can see why you have a spectral overlap, because in absorption promote electron from band conducting band. Emission is the high energy electrons relax back. The emitted photon is energy fairly close. That's why absorption emission are overlap. Okay, so this overlap didn't cause problem. Okay, this is sometimes called self-absorption or self-quenching. The light emitted from the particle can be reabsorbed by itself because of spectral overlap, right? Just like I want to go to Chase Bank, I want to withdraw $100. I got $100. Is that I need to get a 50 back, right? That's kind of happen. So because of spectral overlap, self-absorption, you never reduce energy conversion efficiency from the quantum dots. Okay, how can we address this? So in our group, we thought, how about introduce additional charge, relaxation pathway? We introduced new energy levels inside the band gap, in this case, magnetic dopants, and the light absorbed from the particles ever excited electrons in conducting band, instead of a direct emission, you can have a energy transfer to dopant energy levels. You're not going to have a whole post emission, you have a dopant emission. You look at the y-axis, it's the energy, coordinate. This is much shorter than the band gap, so you can have an emission on the lower energy side, which is a longer wavelength. So I can shift the emission to long wavelengths and have zero spectral overlap. So it can increase energy conversion efficiency, right? Yeah, this is the idea. We dopant there, sunlight absorbed by the host materials, emission from the dopant ions. Okay, and okay, use these particles to make solar condensators. Okay, people use solar condensator for centuries, right? Initially, people use a big mirror to concentrate sunlight to cook, to boil water. But now we can use our functionalized polymer dots, doped polymer dots. We put it in the transparent polymer matrix, and we can concentrate the sunlight. Okay, sunlight absorbed by the host lattice, emission from the dopant. Okay, because different refraction index between air and the polymer, you can have a total internal reflection upon edges of the concentrator polymer, right? You can have a concentrated light at the edges. And now you can imagine if you put a small PV cell here, you can increase the efficiency because of a concentrated light, right? You can see this is a real concentrator we made in our lab. And on the room light, you can see surface kind of transparent edges. It's like an orange color, syracuse color emission from manganese. Okay. And on the UV light, sunlight, you can see it's really bright. And now you can see, if you read the PV cell, you can increase efficiency, reduce the cost. This is, address our initial question. How can we, reduce cost, increase the performance or efficiency? Okay. Okay. So now the important application for functional nanomaterials are photocatalytic reactions. Use nanoparticle as a functionalized, robust catalyst, right? Compared to traditional thermal reaction, photocatalytic reaction usually occur on mild reaction conditions, right? Clean, expensive source of energy, right? Yeah, so if you don't work with photocatalytic reaction, I can just use this simple scheme to show you. Very simple. You start with a semiconductor material, can be bulk, can be nano. Okay, they have a band structure. This is the band conducting band. Light come in, promote electron from the band conducting band. Electron here leave an empty hole behind. Okay, electronegative charge, right? Now, if you have a molecule or species can take electrons, that's reduction reaction. For example, it can reduce the water to form hydrogen field. You can also use a hose, right? The positive charge, like opposite as electrons, you can do oxidation reaction. Okay? The concept is very simple. But the problem here is the lifetime of the electron in conduction band can only be stable for on order of a nanosecond or tens of nanoseconds. Okay? So very fast recombination will occur. Wait the nanosecond time, if you don't use it, they can go back to the low state, right? Because high energy is not stable, they're going to go back. So you can see how challenging it is. If you want to use a simple quantum dot to photocatalytic reaction, right? It comes back with a fast charge recombination. But even though lots of people work on that, okay, it's still doable. Okay, but for ideal photocatalysts, we think we should generate more stable charge carriers. Can be used for further chemical transformation, right? So in my group, how we can get it? What we did is, again, we introduced manganese dopant there. Okay, we manganese dopant here, similar as slide showing the solar condensators, have energy transfer to dopant energy levels. Interestingly, or significantly, the lifetime for the excited state electron associated with the dopant is order of milliseconds. Okay, milliseconds 10 to -3 seconds. You think it's still pretty short, right? But compared to original nanosecond 10 to minus 9 seconds, you increase by 5 to 6 order of magnitude. So we think the dopant particle definitely can provide much more stable charge carriers for further photocatalytic reaction. We have much time window to use electrons for further reactions. Okay? Yeah, so this is our recent work. We developed magnetite and sulfide from dust. We tipped with the platinum and particles on both sides. Kind of a cute downbear structure is a TN image. So the idea is very simple, same as I showed last slide. We use light promote electron, for the host lattice and sulfide, generate charge carriers, electron hosts. Then any transfer curve, we generate much more stable charge carriers associated with the dopant. Then later we have our electron transfer because matter, right? Conductor. Electron transfer to platinum particles provide active sites for future water splitting reaction to generate hydrogen gas. All right. So here's data. If you don't do anything, start with the platinum sulfide. No dopant, no platinum. Yeah, you can generate the hydrogen gas. People report this. Okay. If you don't add dopant, add a platinum nanoparticle, yeah, better. The platinum is very good catalyst. We knew it. But after we add the intermediate step, generate a much more stable carrier, can say boom. We increase the efficiency for about 4.5 times. Okay, so this is the electron transfer. Okay, we do photocatalytic reduction reaction. We can also do photocatalytic oxidation reaction. Okay, so in this work, we developed the magnetite from dots coated with the silica and further decorated with the platinum particles. Okay, so in this case, again, we generate electron host from the host lattice and transfer to magnetic dopant, and after that, we have an anti-transfer to triple state oxygen, which is normal oxygen molecules. Then they can transfer to singlet oxygen. Okay, this is a reactive oxygen species, and we can use the singlet state oxygen molecule to select oxidation for basic aldehyde alcohol to aldehyde. So we found this is a highly selective. We never think acid. If you have a very strong oxidation agent, you can further oxide to acid, right? But we'll stop here. No acid detected in the solution in the product, and the reaction yield is really high. And you can see we can also do anti-transfer to do photo-oxidation reaction. Okay. So when we do the reaction, how many times do I have? Okay, great, thank you. So yeah, try to try to go over the 1 hour time. Okay, yeah. So when we do this, we found an interesting phenomenon because it's an anti-transfer, right? From here to oxygen. Anti-transfer distance dependent. Okay. The longer distance, less efficient in transfer. Short distance, more efficient in transfer. So now say, can we manipulate the dopant locations inside any crystal, either on the surface, in the core, or at specific depths of a nanoparticle? Okay. So we want to go to another level of dopant manipulation. Okay. This is a kind of a very fun. You can see this is how we do research, right? We start with some fundamental question, we make nanoparticles, then we would go to the application. Then based on the application, we further identify some of the key important fundamental question again. Okay. So actually we found we can control the dopant location by directional dopant migration. Okay. So this is my favorite project, I think. What we did, we start with some magnet and sulfide compounds. Magnet is everywhere. We can improve the sulfide shield monolayer by monolayer. We can calculate how many atoms needed for one single atomic layer. Okay. The first monolayer, after that we go to the second monolayer, third monolayer, etc. Very beginning we thought just shear coating, right? Make much more stable compounds. Okay. We're not going to change something else. But interestingly, we found in this observed emission spectrum, This is manganese emission from any transfer. As we increase the shield thickness in the first molecule to 5 more layer, you can see we suddenly have an emission from the host layers. The relatively intensive manganese keeps decreasing. People never seen this before. What happened here? Now we know because manganese emission from host to dopant and transfer, we thought we might have a separate host and dopant somehow, right? So, for example, we're in the same room, very close, we can communicate. Outside building to further away, no any transfer, no communication. So same thing here. So we think many migrate away from the core. And it's really hard to study, right? Because you talk about a few atoms. And we found the ratio between manganese emission and host emission can act as an output gauge for dopant location. This is new tool we did that. This is what we think would happen, right? If you put dopant manganese and sulfide form dots, you're going to replace metal side because manganese metal. The manganese 80 millimeters inside 1092, about 13% size mismatch. Okay, and if you grow zinc sulfide here, zinc 74 picmeters, too small. But when you grow shear to the core, you're not going to have a sharp interface. You can have an alloy interface there. So basically, alloy zinc, zinc can provide intermediate lattice, side for dopant. So here manganese here large size mismatch, too big, but here intermediate, very close to manganese. We think that's what happens, right? We go to anode phase with decreased size mismatch, thermodynamics should be more stable. Okay. Oh, I spent hours or so to join the cartoon here because a couple of years ago I have a high school student working in my lab. Now I tell Michael, I said, Michael, look, we find something new. This is the first direct migration behavior dopant observed for cosmetic crystals. I show this picture. Mike said, what are you talking about? I understand we have a different academic background. I have to use a better approach. I showed this, look, Michael, if you put manganese inside very large lattice, it's hard to approach sulfide, cannot form, bond. That weakly we're not happy. If you put in zinc phase, too crowded. But if you add here, and zinc, intermediate average parameters, you're really happy. So now high school kids can understand our research. Okay, so with your many follow-up work to prove this migration not same as random diffusion, not as a direct injection. We prove that. Okay, we're not talking about this work. Now since we prove this is true, and we work really hard to prove this because some people don't believe this. We thought if it is true, we can achieve not just outward migration, can also achieve inward migration. We can use the alloy shear as a target trap for dopants. This is our original work. For example, we want to have an outward migration. We intentionally group the trap layer. We start with the core dopant crystal trap layer, that is further shield that outward migration to trap layer. If you want an inward migration, we start with on-doped core trap layer, then dopant outside in the shield. We can move the dopant back to the trap layer. So we can specifically control the dopant depth, exact location in a core multi-shield crystals. Okay, now we're limited time, but this is I have to talk about this. This is a very interesting project. I collaborate with Jensen. We use a new type of porous materials, metal organic framework for gas separation and adoption. So we work out how to remove formaldehyde to improve indoor, air quality. Okay. So basically, metal framework, there are two building blocks: metal centers and organic linkers. Right? People reported it can absorb gas molecules, including formaldehyde. But we think, how can you modify, engineer the common mold structure to make a better, filters, right? So what we did is we modified linker with, negatively charged functional groups to increase the, polar interactions with the formaldehyde and CO2. We can increase the gas separation efficiency. Of course, we can also modify the, metal centers But here, just to present data, we found after modification in fluorine, we can have a more, formaldehyde absorbed or separated by the modified MIL11. But right now, we have some issue with, I think, it's related to the surface chemistry interface. How can we efficiently coat it on substrate like fan plate that make a stable device to test this, and at the same time we don't we add some glue there, right? The glue don't block the channels, the holes, to prevent further formaldehyde enter the mold structures. Yeah, we work on it. This is very interesting research. All right, I think it's time to wrap it up. I think basically I can skip this one, but this is my previous group. This is a current group. I can take the point some important students both work on this. Dr. Uni work on peroxide photocatalysis, and your turn work on dopant migration. Project Henry in the back work on cultural peroxide. Then Rachel he did the postdoc. Someone, if anyone knows the post good personal position, appreciate that. Work at DLE, work out photocatalytic reactions, and also need to doping stuff. Okay. And many amazing collaborators, including especially Jason, teaching, family. We work on MOB project. Also work with control on the lead-free peroxide analysis. I really appreciate the support from CFCE and also support from NSF, ASSPRF, and from the Research Institute. All right, and thank you very much for your kind attention.
Thank you.